before we move on to our next type of confidence interval, we need to talk about a new distribution. So when we are performing inference for a single mean, a difference in means, or two means, we use the student t distribution whenever the sample standard deviation S is used as an estimator for sigma. So when I know the population standard deviation, I know how variable the population data is, I use the standard normal. If I don't know the variability of that population data, I don't have a value for sigma, then I'm using the student t distribution. This switch only happens for means. For proportions we don't care, categorical data we don't care, slopes and correlation coefficients we don't care. This change only happens for means, and it's going to happen for intervals and testing later. That same switch. If sigma is known, it is z. If sigma is not known, it is t. So let's take a look at what this t distribution is before we have to use it. So properties of the student t distribution. The first thing is that the graph of the distribution is very similar to the standard normal curve. And all of that comes with it. That means the student t is also bell-shaped. The student t is symmetric about its mean. And just like the standard normal curve, the mean for the student t distribution is 0, and it is symmetric about that value. One of the important differences is that the t distribution has more area, if I could write today, in its tails than the standard normal distribution. It is a wider and flatter distribution. This is because the t distribution has a larger standard deviation than the standard normal distribution. The standard normal distribution has a mean of 0, a standard deviation of 1. The student t distribution generally has a standard deviation that is larger than 1, and it is dependent on something that we're going to talk about in the next point, which is the exact shape of the student t distribution depends on the sample size, and the sample size dictates a quantity called the degrees of freedom. And the degrees of freedom for one variable stats, which is what we're doing now, is just sample size minus 1. The curve is going to be lower and flatter for smaller values of df, smaller degrees of freedom. As the degrees of freedom and our sample size increase, the graph of the t distribution looks more and more like the graph of the standard normal. So I have a graph here, and this tallest peak, this guy way up here, that's our standard normal. So that's z, mean of 0, standard deviation of 1. And then I have two student t distributions. And you'll see that the lowest and flattest guy has the smallest degrees of freedom. His degrees of freedom is 5. And then the guy in the middle, this guy right here, has the degrees of freedom of 13. And you can see the change. There's less area here. It's come inward in the tails and gone upward in the middle. So inward and upward as degrees of freedom gets bigger. So it's going to look more and more like the standard normal, which is kind of tall and narrow. It turns out we can perform calculations for the t distribution just like we did for the normal distribution. So when we calculated critical values, so z critical values, we used inverse norm. For t critical values, we're going to use inverse t. There is one difference, and we'll see it when we run this in the next video with some examples. But if you go second vars and you go to inverse t, you'll notice there isn't a tail command. There also isn't a mean or standard deviation command. It knows for t the mean is always 0, and it knows the standard deviation is calculated from the degrees of freedom, so it does that in its memory. But this guy always assumes that you're finding a t value for an area in the left tail. It doesn't do center areas. So you're going to have to do a little bit of finagling with what you know about the normal curve and you know about the symmetry of the t curve to figure out the area left of that lower critical value. We'll go ahead and do some examples in the next video. If you have any questions about what you saw in this video, feel free to send me an email or drop by office hours. Otherwise, I'll see you in our next video.